Hello everyone, my name is Neha. I am a student of BSc Chemistry Honours 5th semester and I am here for making a video for visually impaired students on the topic molecular spectroscopy. General introduction. Spectroscopy is that branch of science which deals with the study of interaction of electromagnetic radiations with matter. Electromagnetic radiation. The term electromagnetic radiation represents the radiant energy emitted from any source in the form of light, heat, etc. Some important characteristics of these electromagnetic radiations are given below. They have dual character, that is particle character as well as wave character. For example, a beam of light is a stream of particles called photons moving through the space in the form of waves. These waves are associated with electric and magnetic fields oscillating perpendicular to each other and also perpendicular to the direction of propagation as shown in figure 3.1. That is why they are called electromagnetic waves. All electromagnetic radiations travel with the velocity of light. C is equals to 10 into 10 raised to 3 into 10 raised to the power 8 meter per second. The wavelength lambda of the electromagnetic radiation is related to their frequency nu and velocity c. According to the equation, C is equals to mu lambda as the quantity 1 by lambda is called wave number. It is still very common to express wave number in terms of non-SI unit centimeter inverse when lambda is in centimeter and c is in centimeter per second. Frequency nu has the units second inverse. As stated earlier, electromagnetic radiations are made up of photons. Each photon is a packet of energy whose energy is given by Planck's equation E is equals to h nu, where h is Planck's constant. Regions of electromagnetic spectrum. When different types of electromagnetic radiations are arranged in order of their increasing wavelengths or decreasing frequencies, the complete arrangement is called electromagnetic spectrum. The regions into which the electromagnetic radiations have been classified is on the basis of the source and detectors required. These limits are given in table 3.1. The different radiations differ with their physical and chemical effects because they possess different energies, the energy of a photon being E is equals to h nu. Basic features of spectroscopy. Introduction to molecular spectroscopy and its difference from atomic spectroscopy. In case of atoms, when the energy is absorbed, the electrons jump to some outer orbits and they start jumping back with the emission of energy equal to the difference between the energy of the two energy levels, and the result is an atomic spectrum. However, in case of molecules, when the energy is absorbed, it may result into rotation, vibration or electronic transition depending upon the amount of energy absorbed. Just as electronic energy is quantized, that is, there are only discrete electronic levels, energy levels in an atom or a molecule, the rotational and vibrational energies are also quantized. That is, there are only discrete rotational and vibrational energy levels in a molecule. The rotational, vibrational and electronic energy levels of a molecule are collectively called molecular energy levels. The transition of energies can take place only between these levels. The result is a molecular spectrum. When the energy absorbed by the molecule is so large that an electron can jump from one electronic energy level to another, then as the energy required from transition from one vibrational energy level to another is much less and from one rotational level to another is still less, hence the electronic configuration transition is also accompanied by the transition between the vibrational levels as well as the rotational levels. The complete picture of the various molecular energy levels for the first two electronic levels is shown in figure 3.2. Thus, each electronic level consists of a number of vibrational sublevels represented by mu is equals to 0, 1, 2, 3, etc. and further each vibrational level consists of a number of rotational sublevels represented by J is equals to 0, 1, 2, 3, etc. V and J are vibration and rotational quantum numbers respectively. Because of a large number of energy levels involved for transition, it is evident that molecular spectra are much more complex than atomic spectra. However, just as atomic spectra help in the study of the structure of atoms, the study of molecular spectra gives even more information about the structure and properties of molecules, such as bond lengths, bond angles, bond strengths, shapes, dipole moments, etc. Absorption and emission spectroscopy. As explained above, an atom or a molecule has a number of energy levels which are quantized. The transitions take place only between these energy levels accordingly to certain rules called selection rules, as will be discussed later. The expressions for the different types of energy levels of a molecule will be derived later in this chapter. However, at the moment, it is sufficient to know that the transition between any two energy levels can take place in either of the following two ways. The transition may take place from lower energy level to higher energy level by absorbing energy. It is then called absorption spectroscopy, and the result obtained as a result of a number of such transitions is called absorption spectrum. The transition may take place from higher energy level to a lower energy level, thereby emitting the excess energy as a photon. It is then called emission spectroscopy, and the result obtained as a result of number of such transitions is called emission spectrum. In fact, a number of groups of closely spaced lines are observed. Each such group of closely spaced lines is called a band. Thus, a number of bands are observed. We can therefore conclude that whereas atoms give line spectra, molecules give band spectra. In either case, the energy of the photon h nu emitted or absorbed is given by Bohr's frequency formula E2 minus E1 is equals to h nu. Or in terms of wavelength, lambda is equals to c upon nu is equals to hc upon E2 minus E1. Or in terms of wave number is equals to 1 upon lambda is equals to nu upon c in centimeter inverse if lambda is in centimeter or velocity c is in centimeter per second. It may be noted that emission and absorption spectroscopy give the same information about the energy level separations. However, the practical consideration decides as to which technique should be used. Generally, absorption spectroscopy is used as absorption spectra are easier to interpret than emission spectra. Emission spectroscopy is used only when the visible or ultraviolet incident radiations are used. In this chapter, we shall therefore mainly concentrate on absorption spectroscopy. Experimental setup. The instrument used for observing absorption spectrum of a substance is called absorption spectrometer, and its principle is shown in figure 3.4. It consists of mainly four parts, namely source of radiation, a slit to get a fine beam, a monochromator, that is a device for getting monochromatic, that is single frequency radiation, a sample cell, dispersing element which is either a glass or quartz prism or a diffraction grating detector. The nature of the components to be used depends upon the nature of the radiation, that is region of electromagnetic spectrum to be used. Types of molecular energies and Born-Oppenheimer approximation. A molecule usually possesses four different types of energies. These are translational energy, which is due to the translational motion of the molecule, that is motion of the center of gravity. Rotation energy, which is due to the rotation of the molecule about an axis perpendicular to the internuclear axis. Vibrational energy, which is due to the to and fro motion of the nuclei of the molecule without any change in the position of the center of gravity of the molecule. Electronic energy, which is due to absorption of energy by the electrons, resulting in the transition from the lower electronic energy level ground state to the higher energy level excited state. According to Born-Oppenheimer approximation, the total energy of a molecule is the sum of translational, rotational, vibrational and electronic energies, that is E is equals to ET plus ER plus EB plus EE. Further, from the expressions for the above different types of molecular energies, as will be derived later in this chapter and have been used earlier also in the previous chapter, it is found that the translational energy is negligibly small. Hence, Born-Oppenheimer approximation can be written as E is equals to ER plus EB plus EE. Types of molecular spectra. As explained earlier, a molecule has different types of quantized energy levels, that is translational, rotational, vibrational and electronic. The molecular spectra arise due to transitions taking place between these energy levels. The energy absorbed for any transition is equal to the difference in the energies of the two levels involved. It is found that these energies for transition are in order: ET less than ER less than EB less than EE. In fact, the difference between the successive translational energy levels is so small that it cannot be observed experimentally. For this reason, for practical purposes, translation energy is considered as continuous and we do not observe any translational spectrum. The different types of molecular spectra are generally observed depending upon the energies absorbed and the region of the electromagnetic spectrum is which they are observed, as shown in figure 3.11 and are briefly explained below. Pure rotational microwave spectra. If the energy absorbed by the molecule is so low that it can cause transition only from one rotational level to another within the same vibrational level, the result obtained is called the rotational spectrum. These spectra are therefore observed in the far infrared region or in the microwave region whose energies are exceedingly small. The spectra obtained is therefore also called microwave spectra. Vibrational rotational spectra. If the exciting energy is sufficiently large so that it can cause a transition from one vibrational level to another within the same electronic level, then as the energies required for the transitions between the rotational levels are still less, both types of transitions will take place. The result is therefore a vibration rotation spectrum. Since such energies are available in the near infrared region, these spectra are observed in this region and are also called infrared spectra. Electronic band spectra. If the exciting energy is still higher such that it can result in a transition from one electronic level to another, then this will also be accompanied by vibrational level changes, and each of these is further accompanied by rotational level changes. For each vibrational change, a set of closely spaced lines is observed due to rotational level changes. Such a group of closely spaced rotational lines is called a band. Thus, for a given electronic transition, a set of bands is a band system is observed. This set of bands is called a band group or a band system. Each electronic transition gives a band system. The complete set of band systems obtained due to different electronic transition gives the electronic band spectrum of the gaseous molecule. Thus, whereas atoms give line spectra, molecule give band spectra. As much high excitation energies are available in the visible and ultraviolet regions, these spectra are observed in the visible region and ultraviolet region. Raman spectra. This is also a type of vibrational rotational spectrum but is based on scattering of radiation and not on the absorption of radiation by the sample. It is based upon the principle that when a sample is hit by monochromatic radiation of the visible region and scattering is observed at right angles to the direction of the incident beam, the scattered radiation have frequency equal to that of the incident beam, called Rayleigh scattering, as well as frequencies different higher as well as lower than that of the incident beam, called Raman scattering. The difference in the frequencies of the incident beam and that of the scattered beam, called Raman frequencies, are similar to those needed for the vibrational and rotational transitions. However, by suitably adjusting the frequency of the incident radiation, Raman spectra are observed in the visible region. Nuclear magnetic resonance (NMR) spectra. This type of spectrum arises from the transitions between the nuclear spin energy levels of the molecule involving reversal of nuclear spin. When an external magnetic field is applied on it, the energies involved in these transitions are very high, which lie in the radio frequency regions. The method is based upon applying such frequencies on the sample so that it is in resonance with the applied frequency. Electron spin resonance (ESR) spectra. This type of spectrum arises from the transitions between the electron spin energy levels of the molecule, involving reversal of electron spin when an external magnetic field is applied on it. These involve frequencies corresponding to microwave region. Frequencies of this range are applied on the sample to bring the sample in resonance condition. Selection rules. We know that atomic spectra as well as molecular spectra are obtained due to transition taking place between different energy levels. However, such transitions can take place only between definite energy levels and not between any two energy levels. The restrictions thus applied on the transitions are governed by certain rules which are called the selection rules. If these rules are followed, then the transition can take place and it is called an allowed transition. If these rules are not followed, the transition cannot take place and it is called a forbidden transition. The selection rules to be followed depend upon the type of transition in case of molecular spectra. However, the fundamental principles on the basis of which the selection rules are derived is that for a molecule to interact with the electromagnetic radiation and to absorb or emit a photon of frequency nu, it must possess a dipole at that frequency, the dipole moment of which is called the transition dipole moment. The intensity of the transition is proportional to the square of the transition dipole moment. Thus, a transition is allowed only if mu is not equals to 0. For example, rotational transition moment, that is accompanying change in the rotational levels of the molecule, is 0 unless the molecule has a permanent dipole moment. Hence, pure rotational spectra are observed only for molecules which have permanent dipole moment, example NO, CO, etc. A gross selection rule specifies the general features that a molecule must have in order to give a particular type of spectrum. The specific selection rules are generally expressed in terms of changes in quantum numbers for allowed transitions. For example, for the pure rotational transition, the selection rule is delta J is equals to plus minus 1, where J represents rotational quantum number. Delta J is equals to plus 1 corresponds to absorption and delta J is equals to minus 1 corresponds to emission. Similarly, for pure vibrational transition, the selection rule is delta V is equals to plus minus 1, where V represents the vibrational quantum number. Further details of these rules will be discussed at the relevant sections. Width and intensities of the spectral lines. In any type of molecular spectroscopy, the two important characteristics of any spectral lines are how sharp or broad is the line. This is decided by the width of the line. How strong or weak is the line. This is decided by the intensity of the line. Width of the spectral line. If a spectral line is sharp, it will have no width as shown in figure 3.313a. On the other hand, if the line is not sharp, it will have a certain width as shown in figure 3.12b. That is, it spreads over a range of frequencies or wave numbers. Factors affecting the width of spectral lines. The two factors which contribute to the broadening of a spectral line are Doppler broadening and lifetime broadening. These are briefly discussed below. Doppler broadening. This type of broadening occurs due to Doppler effect, according to which in a gaseous sample, frequency of the radiation emitted or absorbed changes when the molecule is moving towards or away from the observer or the observing instrument. Doppler effect is applicable to gaseous samples because according to kinetic theory of gases, the molecules of a gas are continuously moving in a zigzag manner. If the molecule emitting the frequency nu, called the source, is moving away from the observer with a velocity v, the observer detects the radiation of frequency. nu dash is equals to nu upon 1 plus V upon C. If the molecule source emitting the electromagnetic radiation is approaching the observer, then it appears to emit radiation of frequency nu dash is equals to upon 1 minus V upon C. The difference nu minus nu dash is equals to delta nu is called Doppler broadening or Doppler shift. Since in a gas the molecules are moving in different directions with different speeds, some of them are moving away from the observer, therefore the detected spectral line arises from all the resulting Doppler shifts. As the speeds of gas molecules at a particular temperature are given by Maxwell distribution, therefore the shape of the Doppler line is similar to that of Maxwell distribution of speeds as shown in figure 3.12b or figure 3.13. Further, it is found by calculations that if m is the mass of the gas molecule, then at temperature T, the width of the line at half of the height is delta V is equals to 2 nu upon C into 2 kT ln 2 upon m whole under the root. Lastly, it may be pointed out that Doppler broadening increases with increase in temperature because the molecular speeds increase with increase in temperature. Hence, to obtain spectra of maximum sharpness, it is best to work with at low temperatures. Lifetime broadening. This type of broadening occurs in all types of samples, that is gaseous, liquids, solids or solutions. It arises because when Schrödinger equation is solved for a system that is changing with time, it is impossible to specify the energies of the levels exactly as they are changing with time. If on the average a system survives in a state for time tau and the lifetime of the state, then its energy levels are blurred to an extent of delta E, where delta E is equals to h upon 2 pi tau. The quantity delta E in terms of wave numbers, the corresponding quantity called lifetime broadening. Equation 4 reminds us of Heisenberg's uncertainty principle, and the quantity delta E in the above equation is called the uncertainty broadening. From equation 4 we observe that delta E is inversely proportional to tau. Thus, shorter the lifetime of the states involved in the transition, greater is the broadening of the spectral line. As no excited state has an infinite lifetime, therefore all states are subject to some lifetime broadening. The main reason for the finite lifetimes of the excited states is the collisions between the molecules or with the walls of the container. If the mean time between collisions called collisional lifetime, then the width of the resulting line is delta E collision is equals to h upon 2 pi tau collision. In a gaseous sample, the collisional lifetime can be increased and hence broadening minimized by working at low pressures. The transition from an excited state to a lower state is a natural spontaneous phenomenon, the rate of which cannot be changed by changing the conditions. Thus, depending upon the natural limit of the lifetime of the excited state, the broadening that results is called natural line width of the transition. However, the natural line widths are so small that the collisional and Doppler line broadening dominates. Intensity of the spectral line. The strength or intensity of a spectral line depends upon population of states with a particular energy in the initial state, called population density of the state, the strength of the incident radiation, the probability that a transition will take place between the energy levels. The probability of a transition is decided by the selection rules. If the transition is allowed, strong or intense spectral lines will be obtained. If it is forbidden, no spectral line or a weak spectral line will be obtained. Similarly, greater is the intensity of the incident radiation, greater is the rate at which the transitions are induced, and hence stronger is the absorption by the sample. To explain how the population density of the states involved in the transition affects the intensity of the spectral lines, Einstein suggested that the net rate of absorption in the presence of an electromagnetic field, that is incident radiation, is the resultant of the following three processes: stimulated absorption, stimulated emission, spontaneous emission. These are shown diagrammatically in figure 3.14. Stimulated absorption is the transition from a lower energy state to a higher energy state by absorbing suitable frequency from the incident radiation, that is, the process has been stimulated by the incident radiation. According to Einstein, the rate at which this occurs is given by R is equals to B rho, where the constant B is called Einstein coefficient of stimulated absorption and rho is the energy density, energy per unit volume of the radiation at the frequency of the transition. Equation 6 represents the rate of absorption for single molecule. For n molecules present in the lower state, the total rate of absorption for transition rate will be R is equals to NR is equals to NB rho. Einstein suggested that the radiation was able to induce a molecule in the upper state to undergo a transition to the lower state and hence produce a photon of frequency nu. This is called stimulated emission. The rate of stimulated emission is given by R dash is equals to B dash rho, where B dash is Einstein coefficient of stimulated emission. Note that only radiation of the same frequency as required for transition can stimulate an excited state to fall to a lower state. Einstein further suggested that the excited state could return to the lower state not only by stimulated emission but also by spontaneous emission at a rate independent of the intensity of incident radiation. Hence, the total rate of transition to a lower state is given by R dash is equals to A plus B dash rho, where the constant A is called Einstein coefficient of spontaneous emission. Thus, for n dash molecules in the upper state, the total rate of emission will be R dash is equals to n dash into A plus B dash rho, where n dash is the population of the upper state. At relatively low frequencies, that is, for rotational and vibrational transitions, the spontaneous emission can be ignored. Hence, we can write R dash is equals to n dash B dash rho. For equations 7 and 11, the net rate of absorption is given by R net is equals to NB rho minus n dash B dash rho is equals to n minus n into B rho. Thus, the net absorption is proportional to the population difference of the two states involved in the transition. Hence, the intensities will be proportional to the population difference between the two states. At any temperature T, the ratio of the populations of the two states with energy E and E dash can be obtained by applying Boltzmann distribution law. N dash upon N is equals to E raised to the power minus h nu upon kT, where h nu is equals to E dash minus E is equals to delta E. If delta E is large, the ratio n dash upon n will be small. This will imply that the population in the upper state is small. Hence, the only significant absorption will be from the lower state and the stimulated emission from the upper state will also be negligible. Degrees of freedom of motion. Consider a molecule made up of n atoms. Since almost all the mass of the atom is concentrated on its nucleus and the nucleus is very small in size, the radius being of the order 10 raised to the power minus 15 meter, whereas of the molecule the order is 10 raised to the power minus 10 meter. The atoms may be considered as mass points. To represent the mass point, we require 3 coordinates. Hence, to represent the instantaneous position of n points in space, we require 3n coordinates. The number of coordinates required to specify the position of all the mass points, that is atoms, in the molecule is called the number of degree of freedom. Thus, a molecule made up of n atoms has 3n degrees of freedom. According to kinetic theory of matter, when thermal energy is absorbed by a molecule, it is not within the molecule in the form of translational motion of the molecule, internal movement of the atoms within the molecule, that is rotational motion, and vibrational motion. The translational motion of the molecule means the motion of the center of mass of the molecule as a whole. The center of the mass of the molecule can be represented by the three coordinates. Hence, there are three translational degrees of freedom. The remaining 3n minus 3 coordinates represent the internal degrees of freedom. However, as already mentioned, the internal degrees of freedom may be subdivided into rotational degrees of freedom and vibrational degrees of freedom. For a rotational motion, there are 2 degrees of freedom for a linear molecule and 3 for a non-linear molecule, as shown in figure 3.15. Remaining degrees of freedom for the linear molecules are equal to 3n minus 5, and for the non-linear molecule they are equal to 3n minus 6. These describe the motion of the nuclei with respect to the another and thus represent the number of vibrational degrees of freedom. Hence, vibrational degrees of freedom of a linear molecule containing n atoms is equal to 3n minus 5. Vibrational degrees of freedom of non-linear molecule containing n atoms is equal to 3n minus 6. A few examples on the calculation of vibrational degrees of freedom are given below. As a diatomic molecule is always linear, its vibrational degrees of freedom is equal to 3n minus 5. In terms of coordinates, the vibrational degree of freedom represent the interatomic distances and angles needed to specify the geometry of the atomic framework within the molecule. In terms of molecular motions, the vibrational degrees of freedom represent the number of independent vibrational modes that can occur in the molecule, the vibrational energy being associated with each mode. The only one mode of vibration of a diatomic molecule like CO, 4 modes of vibration of linear triatomic CO2 molecule, and 3 modes of vibration of non-linear molecule triatomic H2O molecule are shown figure 3.16. To sum up, for a molecule made up of n atoms, total degrees of freedom is equal to 3n. For the split up of these is as follows. For linear molecule, translational 3, rotational 2, vibration 3n minus 5. For non-linear molecule, translational 3, rotational 3, vibration 3n minus 6. Now we shall take up the study of different types of spectra one by one. Pure rotational microwave spectra of diatomic molecules. Energy levels of a rigid rotator. On the basis of wave mechanics, it can be seen that if diatomic molecules is considered to be rigid rotator, that is like a rigid dumbbell joined along its line of centers by a bond equal in length to the distance r0 between the two nuclei, then the allowed rotational energies of the molecule around the atom passing through the center of gravity and perpendicular to the line joining the nuclei are given by Er is equal to h square upon h pi square I j plus 1. Where j is the rotational quantum number that can have values 0, 1, 2, 3, etc. and I is the moment of inertia of the molecule about the axis of rotation, that is I is equal to m1 m2 upon m1 plus m2 r0 square is equal to mu r0 square, where m1 and m2 are the atomic masses of the two atoms of diatomic molecule and mu is called the reduced mass. Rotational selection rules. According to the selection rules, the transition takes place only between those rotational energy levels for which delta J is equals to plus minus 1. That is, the change in the rotational quantum number is unity. The transition delta J is equals to plus 1 corresponds to absorption and delta J is equals to minus 1 corresponds to emission. In other words, a transition can take place from a particular rotational level to just the next higher or just the lower rotational level. All these transitions can take place with equal probability, whereas all other transitions are forbidden. Types of molecules exhibiting rotation spectra. As already explained, the gross selection rule for the observation of a pure rotational spectrum is that the molecule must have a permanent dipole moment so that it can interact with the electromagnetic radiation and absorb or emit a photon. Thus, pure rotational spectrum is given only by polar molecules. Consequently, homonuclear diatomic molecules like H2, N2, etc., and symmetrical linear molecules like CO2 or symmetrical molecules like C6H6 do not give rotational spectra. Thus, polar molecules like H2O, NO, N2O, etc. give pure rotational spectra. Structural information from rotational spectra, calculation of moment of inertia and bond length from rotational spectra. From the study of rotational spectrum, that is by determining the frequency separation, it is possible to calculate the moment of inertia I of the molecule using equation B is equals to h upon 8 pi square IC. Then, knowing the masses of the atoms present in the diatomic molecule, it is possible to calculate the distance between the atoms R0, that is internuclear distance or bond length, using equation 2. Experimental details of microwave spectroscopy. The source of radiations is a special type of electronic oscillator called klystron. It produces monochromatic radiations of frequency corresponding to wavelength range of 0.1 to a few hundred centimeters. The energies corresponding to these wavelengths are same as required for rotational transitions. The procedure consists in passing the monochromatic energy of the microwaves through the gaseous sample of the substance being studied and measuring the intensity of the transmitted radiation. By varying the frequency of the oscillator and observing the intensity of the transmitted beams, the frequencies at which absorption takes place can be determined from the plot of the transmitted intensity versus frequency. From these data, the structural parameters like the moment of inertia, internuclear distance, bond lengths, etc. can be calculated. Non-rigid rotator, a qualitative description. As explained above, in equation 2, the frequency of rotation of a rigid rotator is given by nu is equals to h upon 8 pi square I j into j plus 1. Thus, the frequency of rotation increases with increase in rotational quantum number j. But increase in the frequency of rotation increases the centrifugal force which tends to move the atoms apart. This implies that the bond length of the diatomic molecule increases with increase in the value of J. Thus, the molecule will no longer behave as a rigid rotator. Instead, it will behave like a non-rigid rotator. Also, it was explained in equation 4 that the wave numbers of the rotational levels of a rigid rotator are given by Bj j plus 1. For a molecule behaving like non-rigid rotator, the wave numbers of the rotational levels are given by Bj j plus 1 minus dj square j plus 1 whole square, where d is called centrifugal distortion constant and is related to the force constant k of the bond as explained later in section 3.31. Thus, when a transition takes place from rotational level j to j plus 1, the wave number of the line produced if the molecule behaves like a non-rigid rotator, will be given by 2j plus 1 b minus 2d j plus 1 whole square. Now as j increases, the factor b minus 2d j plus 1 whole square decreases. Hence, this delta nu bar decreases with increase in the value of j. Isotopic effect. If in a molecule an atom is replaced by its isotope, chemically the new molecule is no different from the original molecule with respect to electron distribution, internuclear distance or dipole moment. However, because of the difference in mass of the isotope, the moment of inertia of the molecule changes. As B is equals to h upon 8 pi square IC, that is I appears in the denominator, it means that if I increases, B will decrease, as the energies or the wave numbers of the rotational levels are directly related to the value of B. Hence the energies of the rotational levels will decrease, that is the energy levels will come closer. Otherwise, 2 as the spacing between the adjacent energy levels is equal to 2B, decrease in the value of B means the energy levels will come closer. From the study of the rotational spectra with isotopic substitution, it is possible to calculate not only the atomic masses of the isotopes but also their relative abundances by comparing the absorption intensities.